Hello, and welcome. I'm your host, Watson Williams, and you're watching Cryptic Creations, where we bring you the not so obvious. In today's video, we're going to talk about my discovery of how to construct a random walk from the digits of pi. Now, I understand that this is not exactly the first time that this has ever been done, but it's something that I did independently and on my own, and we'll be talking a little bit more about the origin, or not the origin for me again, but the first time that this was done. So, first of all, where did I get this idea from to do a random walk with the digits of pi? It all goes back to my video, which is not necessarily a prerequisite for watching this video, but it would probably help if you have the time to watch it. It's right here. As you can see, Kurzweil's blunder, the singularity is not near, and in this video I talk about how, I talk about this function that I came up with last year, and it took me several months to construct this hour and 21-minute video, and but it's essentially the case that I came up with a function or a procedure that allows you to functionalize sequences for statistical analysis, and in so doing, I realized after a while that I don't remember exactly what my thought process was, but I realized that because I was thinking about random numbers, irrational numbers, and I came to the realization that you could take numbers like pi, irrational numbers, and convert them into sequences. And the way that you do that is, so you'll take pi and you convert it into a sequence, and this is going to be a non-decreasing sequence, a sequence that increases. And what these numbers what each one of these numbers represent, or rather what the digits of pi represent for this pi sequence, is each digit in pi represents a delta in between the successive elements in the sequence. For example, there's 3 digits between 0 and 3. There's 1 digit between 3 and 4. There's 4 between 4 and 8, etc. So you just convert, in this way, we can convert any string of numbers. Again, it doesn't have to be pi, but that's the example that we're using. And through the discrete linear difference function, which is in my video, Kurzweil's blunder, in depth, I give an in-depth description of how to execute this function. I give you the rules, the function, and properties of the function, and but you don't really need all of the, or you don't really need the full procedure at first I'm kind of getting a little ahead of myself, but basically what you want to do after you convert or start converting, because you can never finish, right? converting pi into a sequence, but you're going to have each one of the elements in the pi sequence on the number line, and then you will use the path rule from DLDF, the discrete linear difference function, and this will generate a random walk in the plane that is functional in the sense that you're not going backwards, and it passes the vertical line test, and of course DLDF is a function, and the only thing that we're not sure of is whether or not because it's what we're using is the path rule, which states that for successive deltas, you start at the beginning of your sequence, and you look at the delta between the first and the second element, and you compare it with the delta between the second and the third element. And if that second delta is smaller than the first, then you continue down with the sequence, and you start out with the default rule, which always goes down. And it's the case that for sequences with strictly decreasing delta, the graph and the function, the graph that will generate will be all down, and the output from the first element will be equal to the gross length of the sequence, and then the functional output will be just slightly greater than that via the squaring rule. And again, watch the video. Kurzweil's blunder. The singularity is not here, but and so it looks like, because see, this is germ, and then we have our first divergence here. So this is all going to be, this is seed, and then it looks like everything after this might end up being all germ cases. So in that case, the total output would be 5, because this is 4. This is a height of 4, and then you do the squaring rule, which takes you square off at the lowest functional output. But then we don't exactly know if there will ever be a what's called a recovery, which means, because in DLDF you just add everything that goes down. Anything that diverges up is something that you have to subtract out of the function. So that's basically it. You're going to generate a random walk in the plane with the digits of pi using the path rule, the default rule, and the equality rules. And don't forget that the first germ equality case goes up by default, whereas the first equality case, first seed equality case, goes down by default. But that's all a little bit TMI. But for Van, yeah. So the first time that a random walk was generated, apparently, was by John Venn, the creator of the Venn diagram, and that's what he's mostly known for. But he also apparently did a random walk from the digits of pi, only it was treated, each digit was treated as a direction, and then you would follow out in that direction however many, whatever the digit was, that would represent the length that you would go in that direction. And you can learn a little bit more about that here on this man Jeff Thompson's blog page here. It's a random pi walk, and as you can see, it's not functional, but it's a random walk. And I have my own version here, and this is original. I just wanted to get this out there, put it out into the internet, into the universe, and to let people know that this is what I did, or one of the things that I've done. And you know, don't ask me what it's useful for. I mean, this is an application of DLDF. Like, I took the random pi walk as a application of DLDF, and this can be studied. You know, what's going to come out of this? Are we going to find that there's a pattern in the digits of pi? I mean, you know, this is very random looking, but who's to say that there isn't some kind of pattern here? But what I would be most interested in, and again, I don't really have all the time in the world to sit here and look at this. I don't mean in this video, I mean like in general, but like, but what I'm most interested in is whether or not there's a recovery past this point. Or no, I mean past this point, because it's all going up by the path rule, and you always go down. Because look here, like this delta here from 14 to 23 is longer than the delta here, so you go down, and then 25 to 31 is longer than 23 to 25, so you go up, and then and as you can see, like the nature of the path rule is such that you're every time you go down, you can only go down a shorter distance than the distance that you went up before. So in order to go farther down than you went up, each successive delta would have to be smaller and smaller, right? So how could you? So just tentatively, I would say that this is the lowest point. That this is going to be the lowest point on the graph, and so then the output would actually be, or excuse me, the x-axis should actually be 1 below that. So you could just push the graph up 1, and then you would have a square right here, and then that you would hit right there instead of right here. It would be like dun, 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 like that. And then yeah, so that's it. I hope you enjoyed this presentation, and thank you for watching Cryptic Creations. Please subscribe and like, and do whatever you feel comfortable with doing in terms of interacting with Cryptic Creations. I'm here for you, and I will be back as soon as I can with another exciting video. Take care.